Good morning, class. Happy Monday. So, got exam this Friday, and it's going to be a challenge to um, uh, administratively handle the exams this semester because of the hybrid nature of the course and the fact that this is a physics course. So, your problem solving and the work that you do when you are problem solving matters a great deal. And I award partial credit for the work that you show, even if you don't get the right answer. So this leads to a little bit of a challenge, because what I need to be able to do is to collect your answers electronically via Sakai, um, and those are answers to multiple choice questions or numerical questions, problem solving questions, numerical answers. But then I also need to be able to collect your work. Okay, so here's how this is going to go down. Friday, the exam is Friday this week, and it covers 1D and 2D motion, kinematics. So everything through projectile motion. Okay, we're going to start talking about forces today and Newton's laws. That's not on the exam. All right, so everything through projectile motion. Oh, and uniform circular motion. Uniform circular motion, centripetal acceleration, v squared over r, and projectile motion, 2D motion. All right, so there's the sign-up sheet for Friday, the online sign-up, and I got room in the classroom for 12 students, and the first 12 students to sign up can come to the lab on that day to take the exam. And what you'll do is you'll take the exam, and then immediately when you're done with the exam, you'll hand in your exam. Okay. So and then that will be graded. If you're taking the exam remotely, what you're going to need to be able to have is access to Sakai during that hour of class, so you can access the exam questions, and you're going to need a webcam, and the webcam is going to be directed at you while you take the exam, and there'll be a Zoom session that will be active while you're taking the exam. So you'll log in the Zoom, and that way I'll be able to supervise your work in that fashion, and if you have questions, you'll be able to ask me either via the chat window or one-on-one audio communication. Okay, but probably the chat window is the best. Okay, so in other words, you can take the exam anywhere you have internet access, a webcam, and a computer. All right, or you can take the exam in 110. So if you're doing this remotely, you'll submit your answers via the Sakai assignment. It's going to be a quiz or an exam that's posted in Sakai. And then when you're done, you'll either have to scan or take pictures with your smartphone of your written work and submit that to me as well. Okay, so that way the exam will be graded electronically in Sakai, but even if you get a question wrong, I'll be able to look at your work and hopefully award partial credit for the work that you submit. All right, and the honor code will be in effect. You'll be able to have a calculator, scientific calculator. You'll be able to have your equation sheet, the sheet of equations that I post on Sakai, and a pencil or a pen. But that's it. No notes, no using the internet and a web browser, besides using one for Sakai, and no book. Okay. All right, so today I want to start talking about Newton's laws of motion, but I also want to do some conceptual review on motion. So let's do this. I'll spend, it's 1/4 after right now. Let's spend about 15 minutes, 10 or 15 minutes introducing some new material. And then we're going to do clicker questions, but we're going to do this remotely using a website called Poll Anywhere. And we'll see how it goes. Okay, this will be the first time that we use Poll Anywhere. All right, so let's get started with some new material. Okay. Okay, so we've been talking about motion, and now we're going to change gears and talk about forces. And in physics, it's appropriate to think of forces as pushes or pulls. All right, so imagine you can think of many different kinds of forces in your everyday lives. Everything from forces that involve your interaction with objects, and some forces involve direct contact with objects, like pushes and pulls that you would like on a shopping cart, or pushes and pulls that would be transmitted by ropes and things like that. And some forces involve no contact at all, like gravity. Gravity is a force that can act at a distance. All right, so the essence of Newton's laws. Okay, so in the 1700s, Sir Isaac Newton developed the physics that we now call classical physics, or Newtonian physics. He developed this almost single-handedly. And part of the physics that he developed has become known as Newton's laws of motion. And there's 3 of them. There's 3 laws of motion. And I think you can think of these laws of motion as what's a good way of saying this? A summary of the way that things in our universe interact with other things. And really that's what defines all of the interesting stuff in our universe. If the universe was just one particle, it would be a very boring universe. It might as well. But the things that give flavor to our physical world are interactions, when things interact with other things. And all of these interactions are mediated by forces, pushes and pulls. I mean, even the way I'm interacting with you right now is governed by forces. I'm creating sound waves, which push and pull on a microphone membrane in this web camera, which transduces that signal into electrons, which travel through the internet to your speaker, which push and pull, electrical signals push and pull on your speaker, creating sound waves, which then push and pull on your eardrum. So all interactions are mediated by forces. All right, so Newton's laws of motion. The first law I'll make some space here. There's 3 laws, and I think I'll start with the second law of motion. So I'm gonna write out these laws as a sentence, 1 or 2 sentences, nothing mathematical. Just write out what these laws are in words. So the second law can be summarized like this: forces cause masses to accelerate. Forces cause masses to accelerate. Okay. So what this is getting at is this is connecting this new thing, forces, pushes and pulls, with what we've been studying up to this point, or more specifically, accelerations. So forces cause accelerations. Forces cause objects to speed up or slow down or change direction. Because remember, accelerations are vector quantities, so velocities are vector quantities, so the change in velocity could be a change in magnitude, speeding up or slowing down, or a change in direction like we saw in uniform circular motion. All right, let's do the third law now. The third law has to do with interactions between objects. And you might have heard this stated in a number of different ways. Something like every action has an equal and opposite reaction. So let's riff on that wording a little bit here, but we'll be a little bit more careful. We'll say it like this. Every force results in a, let's add another word in here. Every action, I'm changing my mind again. Let's say it like this. Every force acting on an object results in a force reacting back on the object. And I'll think of some other ways to state this law as well as we go through this unit. But one of the most fundamental facts about this third law, Newton's third law, is that it involves, I think, what I'll call action-reaction force pairs. If there's an action force, there's a reaction force. And the two parts of the third law state that the action and the reaction are forces exerted on separate objects. Okay? So herein lies the aspect of the third law which involves interactions. You have two objects that interact with one another. If object A pushes on object B pushes back on object A. So you have an action and a reaction. Every force acting on an object results in a force reacting back on the object. And the second part here is move that down here. The action and reaction forces have the same magnitude but opposite directions. Okay, same magnitude but opposite directions. All right, let's look at the first law. can't believe I forgot I had other stuff on this slide. From GIS. Don't need that. Okay. So the first law is a law that maybe you heard referred to before as the law of inertia. And let's think of it this way. So inertia is sort of a nebulous concept. And I can say that inertia is related to mass. That objects that have more mass have more inertia. But I think the healthiest way to think about inertia is something like this. Inertia is this quality that objects have that allows them to resist changes in their motion. So inertia allows an object to resist changes in their motion, or in other words, inertia allows objects to resist accelerations. Okay, so it's related to mass. I don't think it's fair to call it mass. It's not quite the same thing. But something that has more mass has more inertia, resists changes in motion. So in words, one way you can state the first law is something like this. An object in motion with constant velocity will continue to move with constant velocity unless it's acted upon by a force. So that's a lot of words, but let's write that out. An object, let's say like this, an object in motion will continue in motion with constant velocity So there's two parts there. Constant velocity means constant speed and uniform direction. Constant speed and direction, because velocity is a vector. With constant velocity, unless acted upon by I'm going to write this word, net force. Okay. So the word net will become clear as we develop these theories of motion. All right, so in words, we have Newton's 3 laws written out here. An object in motion will continue in motion with constant velocity unless acted upon by a net force. Law 2 is forces cause masses to accelerate. So you can see that there is a connection between 1 and 2. In a way, Law 1 is just the negative of Law 2. If forces cause masses to accelerate, the absence of forces, or net forces, total forces, cause masses to have zero acceleration, to not change their motion. And that means they would move with constant velocity. And number 3 has to do with interactions between objects. All forces in our universe are due to interactions between objects. Every force acting on an object results in a reaction force back on the object. The action and reaction forces have the same magnitude but opposite directions. All right, so we will stop there for today with the new material, and on Wednesday we will take a look at how to develop these 3 laws of motion mathematically. We'll write down some equations that summarize these 3 laws of motion. All right, so let's work on some concept questions that'll help you for the exam on Friday. All right. Okay, so let me start with Uh, let me see if I can find this. Chrome. So what I got to do now is just give me a second here. Hold on, I'm still here. I'm just trying to find. Oh, wrong keyboard. It's going to be a little bit of hiccups here this first time we do this. Let me come back to the webcam. Okay. But what I'm doing is I've set up. Hold on. I set up a slide on a website called Poll Everywhere. All right. So I want to give you the link to this poll. Okay, so here we go. Hold on. Okay, and there we go. Okay. Okay, so what you need to do is, and I think there's an app for Poll Everywhere too, but you can also go to this website. So this might be a little tricky if you're watching this on your, if you're watching the live stream on a cell phone, this might be a little tricky to do both of these things at the same time. But it's my understanding if you open up a live stream in the YouTube app, you can sort of minimize that live stream in a window and then open up a web browser. Anyways, there's a URL here, pollev.com/JeffreyGroff336. So if you go to that website, you should see a poll question, and it's just labeled generic poll A, B, C, D, E. All right, so let's try this. All right. So just go to that website and enter a response. I think I might need to do. There, I activated the poll. Okay. So if you go to that website, you should be able to enter a response, and just go there and enter something, just to see if it's going to work. Good. All right. So I got 3 responses. 4. Keep going. I wonder if I can see. Just got the total results show on chart. Okay, so that says total. So 7 of you have successfully. Only 7 of you have successfully submitted a response. Okay. Well, there's 8. All right, we got 8. Okay, so let me ask you a question. I'm going to clear the responses here. All right, so don't. And it's my understanding that you can change your vote. You can change what you submit. But I cleared the responses. All right, and now I want to ask you a question. So this question deals with something you would have read, but we haven't talked about in class. All right. And the question is, all right, so here's the question. Which scientist or, yeah, we'll say scientist. Which of the following scientists is most responsible for discovering that all objects falling near the Earth's surface in the absence of air drag, accelerate at 9.8 meters per second squared. So mass doesn't matter. All that matters is the object falling near the Earth's surface in the absence of air drag. So this scientist, this person, was able to imagine a world without air drag, air resistance, and concluded that in that world, all objects accelerate at the same rate due to gravity. All right, and your options are A, Albert Einstein, B, Sir Isaac Newton, C, Galileo Galilei, or D, Aristotle. All right, A, Einstein, B, Newton, C, Galileo, D, what did I say? Aristotle. Okay, I should write this out for you. This is just a test. So A was Einstein. B, Newton. C, I'm going to spell this wrong, Galileo. D, Aristotle. I'm a horrible speller. Okay. So which of these scientists is most responsible for uncovering the nature of free fall as all objects accelerating at the same rate? All right, so I'm looking at your responses, and 2 of you have the right answer. Oh, no, now it just shot up. 4 of you have the right answer, but 6 of you have the wrong answer. Okay? I'll give you a clue. This is probably an apocryphal story, which means it's a fun story, but probably never really happened. But the story goes, this scientist, this person, discovered this by doing experiments by dropping objects off the Leaning Tower of Pisa in Italy. The Leaning Tower of Pisa in Italy. Also, here's a fun fact. Well, now I'm not sure about this. So the answer to this question died the year one of these other individuals was born. I think that's true. Einstein, Newton, Galileo, Aristotle. So I think you can change your vote if you want to. It looks like it worked. All right, you're moving in the right direction. Okay, so the answer is Galileo. Galileo Galilei. So he is most responsible. He was sort of the first physicist, the first experimental physicist. And he definitely did experiments involving rolling objects down inclines. And he noticed the rate of acceleration was a function of the angle of incline. And he hypothesized that if the incline was perfectly vertical, all objects would accelerate at the same rate in the absence of air resistance. And so he was able to imagine a world without air resistance. Aristotle would have explained things like, well, if I drop a rock and a feather, the rock falls faster because it's made of earth and it wants to be with the earth. And the feather falls slower because it's made of part air and it wants to be with the air. Or smoke rises. So he had all these weird ideas, but Galileo's ideas about how the physical world worked were sort of the de facto standard for like 2,000 years. And Galileo was one of the first people to sort of dispel these misconceptions through experimentation, evidence gained through experimentation. So, and I believe within a few years, I think it might have been the same year, Galileo died, Sir Isaac Newton was born. All right, let's do some more questions. All right, clearing your responses, and we're going to go to try to pick some questions that give you All right, so here's a question. Let me make that bigger. There we go. So when throwing a ball straight up, which of the following is true about its velocity and its acceleration at the highest point in its path? A, both are 0. B, V is not 0, but A is. C, V is 0, but A is not. D, they're both 0. Or E, you don't know. Okay? So when you're ready, pick one of these answers. Well, for the first try here today, I think this is going pretty smoothly. I'll give you another 20 seconds here to think about this. At that top spot in this ball's trajectory, what is velocity and acceleration? When it reaches the highest point in its path. All right, so 70% of you got this one right. 70% of those who responded got this right. Actually, now it's 73%. Okay, so that's great. And the correct answer is C. Okay, at the top, V is 0 because the ball has momentarily come to rest. It's in the process of changing direction. But acceleration is not 0. So as the ball goes up, when it reaches the top, it momentarily comes to rest, and then it changes direction. So acceleration is not 0. Acceleration is a constant 9.8 meters per second squared directed downward. And that causes the ball to slow down on the way up, stop momentarily, and speed up on the way down. So at the top of its path, it's changing direction. So if the acceleration was 0 at the top of its path, what would that look like? It would go up and get stuck and just kind of stay there and never move because its velocity is 0, and if its acceleration is 0, that means its velocity is going to be 0 1 second later. It's going to be 0 1 minute later. It's going to be 0 for all time because it's not changing. Acceleration can't be 0 or it would just stick there at the top. All right, let's try another one. All right, similar theme. Oops. Here we go. Alice and Bill are at the top of a building. Alice throws her ball downward. Bill simply drops his ball at the same time, I guess. So Alice throws her ball down. Bill just lets his drop. Which ball has the greatest acceleration just after they release their balls? Okay, so after Alice's ball leaves her hand, and after, hold on, I got to clear your responses, so if you already voted, vote again. Sorry about that. If you already submitted an answer, click it again. Got 2, 3, 4. I think you're learning. 5, 6. All right, 7. Excellent. 8. Excellent. All right. 90% of you got the right answer, and the right answer is C. Neither. They both have the same acceleration because after they leave Alice and Bill's hands, the balls are in free fall. So they're both going to feel the acceleration due to gravity. And importantly, the acceleration is independent of the initial velocity. So Alice's is going to have a higher velocity initially. initially Bill's ball will have a zero velocity, but that's not what the question is about. The question is, how are they going to accelerate? So if the acceleration is 9.8 meters per second squared, let's put some numbers to this. So if Alice throws her ball and the instant it leaves her hand, it's traveling at 5 meters per second downward. 1 second later, it's going to be traveling at 5 plus 9.8 or 14.8 meters per second downward. So it's gained 9.8 meters per second of velocity. That's what it means to say it's accelerating at 9.8 meters per second squared. What about Bill's ball? The instant Bill drops his ball, its velocity is 0. But 1 second later, its velocity will be 9.8 meters per second downward. After 2 seconds, it'll be 19.6 meters per second. Gains another 9.8 meters per second every second it's falling. All right, so which ball will get to the ground first? Alice's. Which ball will be traveling the fastest the instant before it hits the ground? Alice's, because it starts out with an initial velocity, and Bill's starts from 0. But the question is about acceleration, and they're accelerating under the influence of gravity, which is a uniform 9.8 meters per second squared. All right, let's do another one. Let's try this one. This one has to deal with all right, clear your responses. You throw a ball upward with initial speed of 10 meters per second, assuming there's no air resistance. What's the speed when it returns to you? So it goes up, reaches the top, comes back down. What's the speed when it returns to your hand, the moment before you catch it? Oh, so I'm looking at your comments, and Holly says you can do this by text. Wow, that looks cool. Okay, so Holly's trying the text Jeffrey Groff 336 to 37607, and then once you're joined, you just text A, B, C, D, or E. So Holly's doing that. That seems to work. So these, Holly asked, are these sorts of questions going to be on the exam? And I was like, yes. So these are the sorts of conceptual questions that I'll ask you on the exam Friday. So all these clicker questions are posted on Sakai for you to review. Don't forget that. So I probably won't ask you a question exactly like one of these, but this is the spirit of the questions that will be on the exam. Oh, Holly, Galileo question. So yeah, that's fair game too. A question on Galileo, that's fair game. In general, anything that's in assigned reading is fair game for the exam. Now, I'm not cruel. That's not gonna be the focus of the exam. The focus will be things that we discussed in class, or concepts that we discussed in class. All right, great. So let's see, 64% of you picked B, so the plurality of you picked B, which is the right answer. So the best answer here is B. And, this has to do with symmetry. The ball is slowing down on the way up, so it starts out at 10 meters per second, and about 1 second later it reaches the top, and then it's speeding up on the way down. So when it gets back to the level where it was released from, its speed will be 10 meters per second. Now in the real world, there is air resistance. So in the real world, the answer is C. It will be less than 10 meters per second because the air drag saps some of its energy away. But it says, assume there's no air resistance in the problem here. So this is setting up a conceptual question in a realm that is based on the theory of what's going on. All right, let's do another one. Got 10 minutes. Let's try this one. So this one is, which of these velocity versus time graphs are impossible? somebody was quick on the draw on this one. One of these is impossible. Want a clue? So first answer the question, what is the physical meaning of the slope of these lines? What physical quantity is the slope of a velocity versus time graph? And then there's a little bit of calculus peppered in here too. And it has to do with the fact with what does, if the slope of these lines have physical meaning, are there any of these options, any of these lines that have a slope that is impossible? Good, 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 good. All right. So 80% of you picked B. 80% of you picked B, which is the right answer. So how do I know it's B? Objects can't instantaneously come to a complete stop. So you can't be traveling along at like some speed, 10 meters per second, and then go poof, drop to 0, and then poof, drop to negative. You can't be driving along and then instantaneously drop to 0, and then instantaneously drop to negative velocity and start traveling in the other direction. These are discontinuous functions, so the slope at this point is undefined. The slope at this point is undefined. So if slope is acceleration, you've got to have continuous functions. So this is continuous, this is continuous, this is continuous. Anytime you have a discontinuous function, the points of discontinuity, the slope, the derivative, whatever you want to call it, at that point is undefined. You can't instantaneously change speed. All right, let's do some more. Let's see. All right. All right, so here's a vector question. I got to clear your responses. Okay, so if you already voted, vote again. You have two vectors such that the sum is equal to 0. What can you say about the magnitude and direction of these vectors? A is a vector, B is a vector, and they add to 0. What has to be true? And let's say that, there's a trivial answer here, and that's that, well, if A is 0 and B is 0, then the sum is 0. So ignore that trivial solution. When I say trivial, I don't mean easy. I mean trivial in the mathematical sense. Trivial solutions mathematically are answers that are 0. I'm not sure anything in physics is trivial in the everyday meaning of that word. All right, so yeah, 100% of you, same magnitude, but must be in opposite direction. So 100% of you got this one right. All right, we already talked about something like this. If you're adding vectors of magnitude 20 and 40, what's the only possible result magnitude you can obtain? 37, because if the vectors point in the same direction, 20 plus 40 equals 60. If they point in opposite directions, 40 minus 20 is 20. So those two answers bracket the realm of possibility. The answer can't be bigger than 60 or less than 20, and the only answer that is in that range is 37 in this case. So let's try this one. Those of you who came to the recitation will know this right away. I'm clearing your responses, and it's ready to go. So from the same height and the same time, one ball is dropped and another ball is fired horizontally. Which one will hit the ground first? I know you guys who came to the recitation will get this one. Showed you a video too. right, good, great. So the answer is C. They both hit at the same time. And so this is a projectile motion problem, and the answer here is based on the fact that in projectile motion, the vertical and the horizontal components are independent from one another. All right? So if you fire a projectile horizontally, the moment it's fired, its vertical motion looks exactly the same as something that's dropped. In other words, if it's like that homework problem with the marble that rolled off the table. The instant it leaves the table, its velocity in the vertical direction, the y direction, is 0, just like if you drop something. So another way to think about that is if you look at this picture here, the vertical components of the motion look identical, and the horizontal component doesn't influence how it's behaving in the vertical direction. So they're both going to hit the ground at the same time. All right, good job. Let's try this one. Actually, don't answer this one. This is a similar question. If you drop a package from a plane that's flying in a straight line at constant speed, and there's no air resistance, that package is going to fall, but it's going to maintain its same horizontal motion as it had when it was on the plane. So it's going to remain vertically under the plane as it falls. Let's try, you know what, I want to skip this one too. I want to do, when's it going to have the least speed? You should try to figure that out. It's at the highest point in its flight. Because at that moment, the y component of its velocity is 0. All right, so it still has a horizontal component, but the vertical component is 0. All right, so again, if you came to recitation, this should look familiar to you. So the poll is live. Here's a football player kicking 3 punts, trajectory 1, 2, and 3, and importantly, all 3 punts reach the same height, but 3 goes further than 2, which goes further than 1. And the question is, which punt's in the air the longest? Hang time is how long the punt is in the air from the time it leaves the punter's foot to the time it hits the ground. Which one is in the air the longest? 1, 2, 3, or they all have the same hang time? All right, you're moving around a little bit. So half of you got the right answer. Half of you have the right answer. The other half don't. In fact, so no one picked B, which is trajectory 2. But some of you picked 1 and some of you picked 3. Some of you picked A and some of you picked C. And those aren't the right answer. The right answer is D. All right, let's reveal the blue box. All right, and the blue box is telling us to focus on the vertical component. The time a projectile is in the air is determined by the vertical motion, how high it goes. And since all punts reach the same height, they're all going to stay in the air for the same amount of time. So this is a specific question about a specific component of the ball's motion. It's hang time. But remember, there's other components of the motion. There's the horizontal component is obviously different. 3 leaves the punter's foot with the greatest velocity. It's just that the vertical component of that velocity is the same as the other 2 cases. The horizontal component is much greater. Thus, it's in the air for the same amount of time, goes to the same height, but it travels much further downfield, has a greater range. So let's take a look at this one. Actually, we're out of time. Okay. Here's another question that it's based on a similar conceptual understanding. If you have these two projectiles fired from this battleship at the same time, which one hits its target first? And the answer is 2. Even though submarine 2 is further away, the trajectory of this projectile right here is less steep, so it doesn't go as high, which means it's not in the air as long. So 2 gets hit first, and 1 gets hit later. All right, so that's enough for today. I'll see you tomorrow for lab. At the beginning of lab, we'll talk about what you're doing and what's expected for this week in lab, and then I'll see you on Wednesday, and we'll keep talking about Newton's laws. All right, have a good day.